Hello lovelies, in this video we're going to be going through our Edexcel Combined Science Foundation paper for Chemistry Paper 2. So what I want you to do, if you haven't done one of these videos before, is to pause after each question comes up, have a go at the answer yourself, and then play the video and watch us work through the answers together.
Noble gases are monatomic and they are unreactive. Here we're asked to give the group that noble gases are found in. Now this question here is just a recall one. We need to know as a fact that noble gases are found in group 0. So now in part B we're asked to explain why noble gases are unreactive. Now this is again another fact that we should know, but it is helpful to understand it as well. Now all of the elements in group 0, the noble gases, all have a full outer shell of electrons. And considering that things react when they want to get this full outer shell, they're actively trying to gain or lose electrons, if something's already got a full outer shell of electrons, it has absolutely no reason to react. And therefore, noble gases are unreactive, and that's because of their full outer shell of electrons. So here we're given a table which shows boiling point against group 0 element. And you can see here we've got a bar chart, we've got helium, neon, argon, and the rest of group 0. And we're asked to describe the relationship between the boiling point of the noble gases and the number of shells. So here I can see that as the number of shells increase, the boiling point also increases. We've got this positive correlation. So what we're going to say to get the marks is that as the number of shells increase, the boiling point also increases. And that there is our relationship. That's all we need to say to get our 1 mark. As the number of shells increases, the boiling point also increases. Perfect. So now that we've described that relationship, we're asked to explain it. And we've got these words in the box to help give us a little boost here, okay? So as we go down the group, we have more shells. And the more shells we have, the bigger the size of the particles, okay? So we can start and get our first mark by saying the greater the number of shells, the greater the size of the particles. And so now we know that, we can get on to our next point. So when we have a greater size of particles, like a bigger particle, we can say that we have stronger intermolecular forces. So now we've made use of all of our words here. So now we can finish up with our final statement that brings it all together, okay? So finally, we can say that as we have stronger intermolecular forces, we're going to need more heat energy to boil this substance. And so that is why, as you go along that group, we end up having a higher boiling point. So just to recap here, so we know the greater the number of shells, the greater the size of the particles, and therefore the stronger the intermolecular forces. Finally, as a result, we need more heat energy to boil this substance and to overcome those intermolecular forces. Okay, so group 7, such as fluorine, chlorine and bromine, are diatomic molecules. State what the group 7 elements are also known as. So here we're given some options. We're given halogens, noble gases, alkali metals and transition metals. Much like the earlier question about noble gases being group 0 elements, this is just a recall question. So group 7 elements are also known as halogens. So if you don't already know that, do make a note of that and go away and get learning it. So now we're asked to complete the sentence about the group 7 elements. and we're asked to put a circle around the correct answer. Moving down group 7, the reactivity, and we're asked, does it increase, does it decrease, or does it stay the same? So the answer to this is that as we go down group 7, the reactivity decreases. And again, this is another really important fact that we need to know about the group 7 elements. So now we're told that when chlorine reacts with potassium iodide, a reaction takes place and the chlorine displaces the iodine. Here we're asked to explain why the chlorine displaces iodine from potassium iodide. So looking at this, let's have a think of chlorine versus iodine in the periodic table. So chlorine has 3 shells and it has 7 electrons in its outer shell. So we know it has 7 electrons in its outer shell because it's in group 7. Now iodine, on the other hand, has 5 shells, but it still is in group 7, so it still has those 7 electrons in its outer shell. Okay, so we're going to draw on those 7 electrons just to help you see this. We don't need to draw it to get the marks in the question, but just for your explanation, I'm going to draw it. So to get a full outer shell and to react, both of these need to gain an electron. But you see, chlorine has a lot fewer shells than the iodine. And as a result, we're going to have a greater attraction between those outermost electrons we're trying to pull and the nucleus, which is positively charged. And that's going to be much stronger than within the iodine, where we've got that much bigger distance and all those additional shells in the way. So as a result of this, the fact we've got fewer shells and this greater attraction between the outer shell electrons and the nucleus, we can say that chlorine is going to gain electrons more easily than iodine. And that there is the reason why chlorine is going to displace the iodine from potassium iodide. So just to summarise, our 3 marks, the first mark are going to be stating that there's fewer shells in chlorine than iodine. Our second mark is explaining there's a greater attraction between the outer shell electrons and the nucleus of chlorine than iodine. And finally, that final mark is just expressing that chlorine will gain an electron more easily than iodine. Hydrogen peroxide solution H2O2 decomposes on addition of a catalyst. The equation for the decomposition of hydrogen peroxide solution is shown below. Here we're asked to complete the equation by adding the state symbols in the space provided. Well, here there should be some hints through the question. So you can see in the opening line it said hydrogen peroxide solution. And whenever we have a solution, we should know that it is aqueous. And so that means that in this balanced symbol equation, next to the H2O2, we're going to put AQ, which represents aqueous. Now, for the next 2 parts, the H2O and the O2, we don't have any hints, so to speak, but we should know that water is a liquid in its standard state, and oxygen is a gas. So that means that next to the hydrogen peroxide we have aqueous because it's a solution, water is a liquid, and oxygen is a gas. So now we're asked to complete the sentences to describe a catalyst. Use the words in the box to help you. So let's have a look at these sentences then. So a catalyst is a substance which something the rate of reaction without being used up. So it's important that we know that catalysts actually increase the rate of reaction without being used up. So it speeds them up and makes them go faster. They do this by providing a different pathway with a something activation energy. Now the answer to this one is going to be a lower activation energy. And that means that less energy is required to start this reaction, which means it's more likely to have enough energy at any one point to start off that reaction. So again, those are a perfect couple of sentences about catalysts. If you're not familiar with those, then do turn them into a flashcard and then you'll have perfect notes. So here we're told that the apparatus shown in the diagram below was set up at 25 degrees C to measure the rate of decomposition of hydrogen peroxide. The following procedure was followed. 50 centimetre cubed of hydrogen peroxide solution was added to a conical flask. A measuring cylinder was filled with water and then inverted in the water trough. That's what we have just here. A rubber bung was connected to the conical flask, which is what we have here. And the delivery tube was placed in the inverted measuring cylinder. The volume of gas displacing the water in the measuring cylinder was measured and recorded every 10 seconds. And here we've got a nice table of the results. Every 10 seconds, what that volume of gas measured is. Here we're asked to use the results in the table to plot the points on the graph 1 below. So let's have a look at this then. So we need to plot a point where the time is 0 and the volume is 0. And that gives us a point just here at 0, 0. Next up we have 10 seconds and 27 centimetre cubed. So notice what each little square in this axis represents. You can see that because there's 5 squares going between say 20 and 30 or 10 and 20 and so on, each little square must represent 2. So when we want to plot it at 27, it's going to have to be halfway between the square of 26 and 28. So here we've got 10 and then 27 will be around about here. Then we've got 20 and 45. Again, that's going to be the halfway point between 40 and 50. We've got 30 and 60, which will be around about here. We've got 40 and 70, which will be here, much easier ones to plot there. Then 50 and 50. Then we've got 60 and 87. Let's be really careful again of the scale. And 70 is 90. And 80 is 90. So there we've plotted our points. Our next part of the question asks us to circle the anomalous point. An anomalous point is one which doesn't follow the trend or the pattern that you can see. It just doesn't look right. And if you look at this graph here, I can see this point doesn't seem to follow the pattern that the other points are following. So I'm going to class that one there as the anomalous point. Now in part 3, we're asked to draw the line of best fit. Now here, rather than being a line, you can see this is a curve. And we're expected to know when a curve is suitable or when a straight line is suitable. And here I can certainly see a nice smooth curve would work out perfectly. Now an important thing to know in these cases is that when there is an anomalous point, we do not include that when drawing our trend line. So here, if I draw my line of best fit, it will start at that 0, 0, and it's going to go along. I'm going to form this nice curve here. And that looks brilliant. So I'm very happy with how that curve has come out. There is my line of best fit. So now we're told that the procedure above was repeated, but this time a catalyst of 1 gram was added to the hydrogen peroxide solution. The volume of gas evolved every 10 seconds was measured and recorded. The results were plotted on the graph 2 below. The rate of this decomposition reaction can be changed by altering various parameters. In part D here, we're asked to draw a curve on the graph of 2 on the previous page to show the volume of gas that forms this time at a higher temperature. So everything else is the same. We've just changed the temperature and we're using a higher temperature. Well, what we need to know here is that we're still going to make the same volume of gas in the end because we still have the same amount of reactants. However, what will change is we're going to make it quicker. As a result, we want to draw a curve that is going to be steeper, but is going to end at that same point. So the curve will look something like this. And those are going to be the 2 main things that the examiner looks for here. One is that the curve has a steeper gradient and it's going to reach that plateau, that flat part, faster. However, the second mark will be understanding that that plateau is at the same point. It doesn't go any higher, it doesn't go lower, it's the same point. Okay, so for part E now, we're asked to tick 2 correct boxes that describe and explain the effect of decreasing the concentration of hydrogen peroxide solution. So we've got less concentration, and let's visualize that. So if we originally had this many particles sat in a box, whizzing around the place, colliding with each other, but now we have less because we have less concentration, we've got less particles in this solution. We need to think, what effect will having less particles in our solution have? And what's going to happen is the collisions are going to happen less frequently. A bit like walking down a busy street versus walking down a really empty street. You're not going to bump into anyone very much if it's a really empty street where there's not many people walking down it. Whereas if it's a crowded city street, you're going to be bumping into people every second. So when we decrease the concentration, there's fewer particles, and therefore there is going to be less frequent collisions with the catalyst. And a knock-on effect on this fact that we have less collisions taking place, is that the rate of reaction will decrease. And those are our 2 points that we want to make to explain the effect of decreasing the concentration of the hydrogen peroxide solution. Here we're told that the experiment was repeated at room temperature and pressure, but this time 50 centimetre cubed of 0.05 centimetre cubed hydrogen peroxide was used. We're asked to calculate the mass of hydrogen peroxide in the 50 centimetre cubed solution. So we know the concentration is 0.002 grams per centimetre cubed. And this means that 1 centimetre cubed of solution comes in at 0.02 grams of hydrogen peroxide. So if we have 50 centimetre cubed of it, then we have 50 times that 0.002 grams of hydrogen peroxide. And so as a result, we end up with 0.1 grams of hydrogen peroxide. And that there is our answer. Crude oil is a mixture of different alkanes. In its original state, it's not very useful as different alkanes can have very different properties. The graph below shows how boiling points change dependent on the relative length of the hydrocarbon chain, measured in terms of the number of carbon atoms. Here we're asked to describe the trend shown by the graph. And whenever we get a describe question, we need to know that we're being asked to say what we see. We need to explain what comes up in the graph in as much detail as we can. So looking at this graph, I can see something very obvious to start off with, which is going to get me my first mark. I can see that as the number of carbon atoms in this chain increases, going from 1 carbon atom all the way up to 10, I can see that the boiling point also increases. You can see that when it was 1 carbon atom, it was about minus 160, and then by the time we had 10, it'd gone up to around 160. So the second thing we can say, I've got my easy mark, is looking at it in a bit more detail. And I can see that when I have a small number of carbon atoms and it's increasing there, say from 1 to 2, I can see that the boiling point is going to increase more rapidly than when we have a longer carbon chain and we're going from, say, 9 carbons to 10 carbons. So I can say here that the boiling point increases more rapidly as we increase with molecules with fewer carbon atoms compared to molecules with greater numbers of carbon atoms. And so that would be my second mark for giving that extra bit of added value to my answer. So we need to get across the fact the number of carbon atoms increases and the boiling point increases, also that this happens more rapidly when we're dealing with fewer carbon atoms. Now we need to explain the trend shown by the graph. And whenever we have an explain, we need our science, okay? Describe is just say what we see. But explaining, we need to use our science to give an explanation. So we're explaining why the number of carbon atoms increasing affects the boiling point. Well, hydrocarbons with more carbon atoms, so longer hydrocarbons, are going to have stronger intermolecular forces. And that's the thing that pulls one of these molecules to another. Now, when we have more and stronger intermolecular forces, we're going to need to put in more energy to pull apart these molecules. So stronger intermolecular forces require more energy to overcome this force of attraction. And as a result, we're going to see that we have a higher boiling point. And so that's what we need to get at as part of our explanation here. So we need to express that we understand that hydrocarbons with more carbon atoms have stronger intermolecular forces. But then we need to link that now back to the boiling point, which was shown in the graph. So we need to make it clear that stronger intermolecular forces are going to need more energy to overcome, and therefore we're going to have a higher boiling point because a higher temperature means more energy. Here we're told that crude oil can be separated into different fractions, which are small groups of alkanes with similar lengths, using a process called fractional distillation. These different fractions have similar enough properties for them to be useful. The table below shows some of the different fractions obtained using fractional distillation and the corresponding carbon chain lengths. So as you can see here, we've got this diagram of the fractionating column where fractional distillation takes place, and you can see the fractions that are produced in it. So now we're asked to complete the sentences to explain how the different fractions in crude oil are separated. So let's have a go at filling in these blanks using the words in the box. So here we're told that the fractionating column has a temperature gradient. It is something at the bottom and something at the top. So we need to know that in a fractionating column, it is hotter at the bottom and it is cooler at the top. So that will be how we start this off. And we've already got 2 marks then. So the fractionating column has a temperature gradient. It is hotter at the bottom and cooler at the top. The crude oil is heated, turns to something and rises through the fractionating column. So the thing that crude oil turns to is vapour. So completing the sentence, we have the crude oil is heated, turns to vapour and rises through the fractionating column. As they rise, they something when they become something enough. So we need to think what's going to happen to that vapour of that crude oil. And when vapour gets cool, it condenses. So what we want to say here is as they rise, they condense when they become cool enough. And that there will be our completed 5 marks. And then the fractions then leave the column at different points. And actually, if this is a topic you don't feel very sure on, these few sentences are actually very helpful. They're very simplified, maybe even more simplified than your textbook. So maybe if you do find this topic challenging, maybe stop the video for a moment and write some notes on this, make a flashcard and get learning these few sentences all about fractional distillation. For part D here, we're asked to complete the sentences by circling the correct option. So here we're told, as you move up the fractionating column, the flammability, does it increase, decrease, or stay the same? So flammability is how easily it will ignite. And as we go up this column, you can see we're changing from things like diesel to petrol to gas. Now the flammability is going to increase as we move up this fractionating column, and that's a fact that we need to know. Then we need to think about viscosity. Viscosity is the ability of a substance to flow. So if it's very thick and sticky, a bit like treacle, it has a high viscosity. Whereas very thin liquids like water or gases even flow very, very easily, and they're going to have a very low viscosity. And as you think about moving up this fractional distillation column, you start with bitumen and oils towards the bottom, and you go up to thinner and thinner liquids until you eventually have a gas. So as a result, we can say that the viscosity decreases as you go up the fractionating column. Now again, both of those are facts we're just expected to know. So if you're not familiar with them, then do stop for a moment and make a nice flashcard on them, and it will really benefit you in the long run. So some alkanes are combusted to release energy. Ethane is an example of an alkane. Here we're asked to complete the dot and cross diagram for ethane. So this here is a covalent dot and cross diagram, which means that all of the overlapping regions that we can see are areas where we have a shared pair of electrons. Now, if we remind ourselves of the periodic table, we should be aware that hydrogen has 1 electron in its outer shell and carbon has 4 electrons in its outer shell. Both of those numbers correspond to the group that they are in. So all of the carbons and the hydrogens here want to gain a full outer shell. Now for hydrogen, to get a full shell, because it's the first atom with just 1 proton and 1 electron in it, a full shell would just equal 2 electrons. Whereas in carbon, as in anything beyond hydrogen and helium, we're going to have a full shell, meaning 8 electrons. So what we can start to do here is start to fill in the information that we know that we have. So we know that carbon has 4 electrons in its outer shell. It's got 1, 2, 3, 4. And we know it needs to have 8, but we'll worry about that later. So that carbon has that total of 4 electrons in its outer shell. Now let's complete it for this other carbon too. So we've got 1 electron, 2 electron, 3 electron, and then the 4th electron is going to get shared with the other carbon. Now looking at this actually, I can see that each carbon now, because it's sharing one with the other carbon, now actually has 5 electrons in its outer shells. So it's getting a little bit closer to that number of 8 electrons that we need to have in the end. So now let's look at the hydrogens. So each hydrogen has 1 electron in its outer shell, and it needs to gain 1 more to get a full shell. So if each hydrogen puts 1 electron into the shared region, see how it gets another one back from the carbon. So actually it gets that 2 electrons that it needs. And that is true of all of these hydrogens. It puts 1 in and it gets 1 back. And that's an important thing to remember with these dot and cross diagrams. If something needs to gain 1 electron, it can't just take without giving. It has to give 1 to take 1 back from another substance. And so we're going to see that throughout, that we've got all this sharing going on. So doing a final check, I can see that I have 8 electrons in this pink ring for this first carbon atom. I can see I also have 8 now in the outer shell of the second carbon atom. And I can see that each and every one of these hydrogens now have 2 electrons in their outer shell, and therefore that also has a complete outer shell of electrons. So now we're asked in part F to complete and balance the equation below to show the complete combustion of ethane. So the important thing here is that we've said complete combustion, because it's important that we know that whenever we have complete combustion, we always get 2 substances. We always get carbon dioxide and water. And now that we know that, we've got 1 mark because we've got our correct products, but now we need to balance the equation. And to do that, if we have a look at, say, the C2H6, our hydrocarbon in this question, you can see that there's 2 carbons within there, and there's no carbons in the oxygen. So that must mean that we have 2 CO2s to give us the 2 carbons to balance with the reactants. Then with the hydrogens, I can see that I have 6 hydrogens in ethane. 6 little hydrogens here. So in the products, I can see I have H2O. So I need 3 H2Os to get the 6 hydrogens that we need. So now that we have this, it is balanced. And we can double check the oxygens if we want to. So we've got 3.5O2, that gives us 7 oxygens. Whereas over on the other side, we can see that we have O2 times 2, so that gives us 4. And then 3 of these O's, which gives us another 3. And then we have 7 oxygens in total. So there we are, we have a fully balanced equation. The really important thing to take from that particular bit is that when we have complete combustion of a hydrocarbon, we always end up with 2 products, carbon dioxide and water. And then after that, it's just a case of balancing. Here we're told that complete combustion is preferred in industry to incomplete combustion as a method of releasing energy from fuels. Here we're asked to tick 2 boxes to identify 2 reasons why incomplete combustion is not preferred over complete combustion. So we need to look through this and work out why would industry not be happy enough with incomplete combustion. And there's 2 reasons here. So one is that carbon monoxide gets produced. So remember we just said that complete combustion, we always make carbon dioxide and water. However, if there's not enough oxygen present, as is the case with incomplete combustion, we don't necessarily make carbon dioxide. In addition to carbon dioxide, or maybe instead of, we make carbon monoxide, which is CO. And the issue with carbon monoxide is that it is a toxic gas. And so we don't want to be releasing that into the atmosphere. The second reason why incomplete combustion is not preferred over complete combustion is quite simply that less energy is produced. So for this question, and for your exams, it's very important that you know that 2 of the disadvantages of incomplete combustion and why we want to avoid it at any point that we can is that carbon monoxide is produced, which is a toxic gas, and also less energy is produced. Another thing we could say, which wasn't here in these options, is that soot is often produced as well, which is pure carbon. So whenever you see a black smoke coming from a combustion, that means that we likely have some incomplete combustion happening here. Here we're told that cracking is an important process carried out on longer chain hydrocarbons after fractional distillation. We're asked here to tick the correct box to show what atoms are found in a hydrocarbon. Now to answer this, let's just look at the name, hydrocarbon, and let's have a think about that. Because really the clue is in the name. The hydro bit refers to hydrogen, and the carbon bit of the name obviously refers to carbon. And so as a result, a hydrocarbon is composed of only carbon and hydrogen, and that's your answer. So now we're asked to give 2 uses of the products of cracking. And remember when we crack a long chain hydrocarbon, we get a shorter alkane and an alkene. Now that shorter alkane can be used for fuel, whereas the alkene can be used to make polymers and plastics. And so that would generally be how we'd want to answer a question like this. That's a good standard answer, so you could always turn that into a flashcard. So now we're asked to complete the equation for the cracking of dodecane, which is C12H26. And this is almost like a maths problem because we need to make sure that on each side of the arrow we have the same number of carbons and hydrogens. So if we start by looking on the left-hand side of the arrow, we can see we have 12 carbons and 26 hydrogens. Whereas on the other side, you see we have 2 C3H6s. So we've got a C3H6 and another C3H6. Now, the importance of that is that we can combine those to see how many carbons there are in total from those 2 propene molecules. So we have 6 carbons and we have 12 of the hydrogens. Now that, of course, is on the right-hand side of the arrow. So you can see we need more carbons and we need more hydrogens on that side of the arrow. And to work out how many we need, let's work out what the 12 carbons is on the left minus the 6 carbons on the right. And you see we get 6 carbons left. And the same with the hydrogens, the 26 hydrogens that we currently have on the left. Let's subtract the 12 we have on the right to see how many more we need. And you can see we need 14 more. Now, as a result, let's turn that into a molecule. We need a molecule of C6H14. And that there will be our final answer. That is our completed equation for the cracking of dodecane. Here we're told that cracking is involved in the commercial production of petrol, which is used to fuel many cars. However, the use of petrol as a fuel in cars has had many environmental impacts, which have led to the development of other fuels such as hydrogen. One of the environmental problems that's been developed due to the use of petrol as a fuel in cars is acidic water in lakes and rivers, which has led to a decline in the populations of fish. So here we're asked to explain how the use of petrol as a fuel in cars could have impacted the population of fish. So what this comes down to is in these fuels there are impurities, and those impurities can contain sulfur. Now, as a result, when we burn this fuel, the sulfur can react with the oxygen in the air to form sulfur dioxide. So that's our first point. Impurities in the fuel may burn to form sulfur dioxide. So now that there's sulfur dioxide being released in the air, it can dissolve in rainwater and as a result form acid rain. And this is our second point that we need to get across here. The fact that we're going to produce this acid rain due to the sulfur dioxide dissolving in the rainwater. So now it's that final conclusion. How does acid rain lead to these fish dying? So this acid rain is going to enter the lakes and rivers where these fish live, and it's going to make them more acidic. As a result of that acidic condition, the fish will die. And that's our final point that we need to get across in this question. The fact that that acid rain will enter the lakes and rivers, making them more acidic, which is not a suitable condition for the fish to live in. And that's now the end of this question. Good work. And let's have a look at the next one. Here we're told that Earth's early atmosphere was composed of carbon dioxide, water vapour and oxygen in a very different amounts to what is now present in the modern atmosphere. You can see there used to be a large amount of carbon dioxide and now there's 0.04%. Water vapour used to be present, but now there's only a trace amount of it. And oxygen, they went from being a very small amount in the early atmosphere up to 21% of our current atmosphere. Here we're asked to explain why the amount of oxygen in the modern atmosphere has decreased when compared to the early atmosphere. Why is there only trace amounts now compared to it being present in larger amounts in the past? So the main reason for this is that there used to be a lot of volcanic activity, much more than there is today. And this volcanic activity produced water vapour, which resulted in higher levels of water vapour. So as the Earth eventually cooled, the water vapour that was present due to all this volcanic activity ended up condensing, and that as a result removed the vapour from the air, and it eventually became the oceans. So that is the main set of reasons as to why the amount of water in the atmosphere has decreased. There used to be a lot of volcanic activity producing water vapour, there isn't now. And also, as the Earth cooled, that water vapour condensed, removing it from the air and making the oceans. So now we're asked to explain how the presence of plants led to these changes in the composition of the atmosphere. These changes being the increase in oxygen and the decrease in carbon dioxide. So a reason for this is that algae and plants ended up evolving. And these algae and plants can carry out a process known as photosynthesis. Now, photosynthesis is a really, really important process. Photosynthesis ends up taking in carbon dioxide from the atmosphere, which has a knock-on effect in decreasing the levels of CO2. And as a result, they also produce oxygen, which increases the level of oxygen in the atmosphere too. So you can see here that these algae and plants had a massive effect. Now, these photosynthesizing plants and algae maybe got eaten by animals or died themselves. And when they died, what would happen is they could eventually, over a very, very, very long period, but eventually get turned into fossil fuels. And those fossil fuels lock away the carbon dioxide, so it's no longer in the atmosphere. And that also ends up reducing that amount of carbon dioxide that is currently in the atmosphere. So you can see here that there's a lot of reasons why the presence of plants led to these changes in the composition of the atmosphere. So just to run those through one last time. The first thing we want to say is that algae and plants evolved and carried out a process known as photosynthesis. Then we want to explain the fact that the photosynthesis took in carbon dioxide, lowering those levels of CO2, and released oxygen, which increased the levels of oxygen. And then we wanted to explain that the plants and the animals which ate those plants would have eventually died and over a very long period got turned into fossil fuels, which also has that effect of decreasing the CO2 in the atmosphere. And there we have it. Those would be our 4 marking points to explain how the presence of plants led to these changes in the composition of the atmosphere. So here we're told that nitrogen is also present in the modern atmosphere. We're asked to tick the box to identify the proportion of nitrogen in this modern atmosphere. Now this is something that we are just expected to know. So the approximate proportion of nitrogen in the modern atmosphere is 80%. So touch under that really, 80%, and that is the number that we're expected to know to answer this question. Here we're told that global warming is the long-term increase of the Earth's overall temperature. The graph below shows the average global temperature and carbon dioxide concentration from 1900 to the present time. So we're told that global warming is widely accepted to be due to the increase in the concentration of certain greenhouse gases in the atmosphere. And this question here wants us to name 2 greenhouse gases. So this again is just a case of recall. Now there's 3 main ones that I would suggest that you should know. First one would be carbon dioxide, which is probably the most talked about one. Next one is methane, which comes from cows. And the last one is water, which often trips students up because you think water vapour is fine. But no, water vapour is another one of these possible greenhouse gases as well. So we could pick any 2 of those, carbon dioxide, methane, or water vapour. Now we're asked to explain how the presence of these gases in the atmosphere can lead to an increase in Earth's overall temperature. So to explain this, we need to understand that from the sun comes quite a short wavelength of electromagnetic radiation. And this shorter wavelength electromagnetic radiation is going to be able to pass through the Earth's atmosphere. So let's imagine we've got our shorter wavelength radiation comes from the sun, hits the Earth. Now we've got this layer though of carbon dioxide and these other greenhouse gases surrounding the Earth's atmosphere. So this shorter wavelength EM radiation will pass through the Earth's atmosphere, but then it gets absorbed by the Earth. And it's essentially going to make the Earth a bit hotter while it's there, okay? So it's heating up the Earth a bit. Now, as it warms up the Earth, some of that energy is going to get dissipated elsewhere. So what the result of that is that we're going to re-radiate some infrared radiation which has less energy and therefore a longer wavelength than the radiation that came in. So it's going to come out now looking a bit like this. It's going to have that longer wavelength than the radiation that came in. So now that we've got this to think about, we can see that this longer wavelength infrared radiation is actually going to get absorbed by those greenhouse gases in the atmosphere, which means that it won't be able to return out to space. Now, once it gets absorbed by the atmosphere, then the atmosphere is going to re-radiate it back to the Earth, can't escape back out into space, and as a result, it's going to increase the temperature. So that heat just gets radiated back to the Earth, increasing its temperature. This works in the same way as to how if you're in a car and the windows are shut, how the car can get hot. It's because the radiation can go in, but once it goes into the car, heats up everything around it, the radiation that gets re-radiated is of a lower energy, a longer wavelength, and it can't actually escape those glass windows, trapping the heat within. The greenhouse gases are acting very similar to those windows, and this is why this is called the greenhouse effect. It works in the same way to how the glass of a greenhouse or a car could end up keeping us hotter. And this is exactly what happens with that layer of greenhouse gases surrounding the Earth. So now we're told that some people are concerned that historical data on average global temperatures and carbon dioxide levels are unreliable. And we're asked here to suggest why this might be the case. So there's two main reasons here, and either of these would get us our mark. One of them is that there used to be a lack of accurate measuring instruments and methods. Of course, science has improved all of our measuring instruments, they're getting better and better. Maybe the lack of them would mean that the data isn't as accurate as we would have hoped. So, a second thing we could say is that not all locations around the globe has always been accessible, and some maybe are still not accessible. But over time, more and more locations around the globe have become accessible, and so we're able to go there and gather data. So a second thing we could say about historical data is that because not all locations were available and accessible, maybe that could mean that we have some unreliable data from the past as well.
Well done for making it to the end of this paper. I'm really, really proud of your hard work. Please remember to get everything that you didn't get 100% on flashcards and then go over those to help with your revision. Ouch! This is why in some videos I explain scratches.